Welcome to part two of KIN 425 for January 20th. This is just like a little cartoon picture here of the one thing I don't like about face masks is that I always forget them at home. Uh, and then when you go to a place that requires face masks, you got to return home to get your mask. So this is a little cartoon that explains that situation. So to continue with the review here of muscle contraction, I've got a couple of questions here. Which enzyme would increase the speed of contraction? Myosin actin crossbridge formation. The correct answer here would be your myosin ATPase. That allows for a faster breakdown of ATP at the myosin head, and that activates the myosin and allows you to have a faster binding with actin. Second question, what enzyme would increase the speed at which a muscle relaxes? The correct answer there is your sarcoplasmic reticulum ATPase. So that ATPase is responsible for breaking down ATP and pumping calcium back into the sarcoplasmic reticulum, and that increases your rate of relaxation. Couple of other review questions here. If you release more calcium from the sarcoplasmic reticulum, what happens to the force of muscle contraction? So to show what happens here, I'm going to make a graph on this whiteboard here. So we've got force on the y-axis, and then you've got calcium concentration on the x-axis. So as you get more calcium released into the muscle fiber, the calcium binds with troponin. That lifts tropomyosin off of the actin, allows myosin to form cross bridges with actin. So the more calcium we have released, the more troponin gets bound with calcium, and you get a greater number of sites on actin that are exposed to myosin, so you get greater cross bridge formation. And with that, you get an increased force production. So the higher the calcium concentration, the greater troponin is going to be bound with, the more troponin is going to be bound with calcium, and you're going to get a higher force output with a higher calcium release. The second question here, if all the troponin in a muscle fiber is bound with calcium, and then more calcium is released from the sarcoplasmic reticulum, what happens to the force of muscle contraction? So at this point, you have a ton of calcium that's been released. All the troponin are saturated with calcium, and that would result in a plateau of your force output. Despite the fact that you're getting more calcium released, there's no longer an increase in force output. So this part of the graph represents a part where more troponin is bound with calcium. And that's causing the increase in force of contraction. And then this point where it starts to plateau, that plateau is caused because all the troponin are saturated with calcium. So all the troponin are bound with calcium. So now you've got a greater calcium release, but the calcium doesn't really have anywhere to go, so it can't bind to any more troponin. So you get this plateau in force output at that stage. So that's your force calcium relationship, and that's the explanation for why it increases, and also the explanation for why it plateaus. So this is a bit of a review of what I went over last day, and it's how the average motor neuron and motor unit size change as you age. So the quick answer to this question is that the average motor neuron size decreases because you're losing the fast twitch motor neurons as you age. the average motor unit size actually increases as you age. And the increase is due to the denervation reinnervation process that occurs as the motor units change with age. So I'm going to take you through that process, and these are slides that I showed you during the in-person or live, not in-person, but the live presentation that I gave on Monday. So here's just an example of two motor units, your slow twitch motor neuron, fast twitch motor neuron, innervated with to their muscle fibers. So you've got two motor units in this example. The motor unit size is defined by the number of muscle fibers that are located in the motor unit. So for example, this motor neuron is larger than this motor neuron, but this motor unit size is the same as this motor unit size because both motor units contain 3 muscle fibers. So we're starting off with an average motor unit size of 3, and we have a large and a small motor neuron. So with aging, you tend to lose the large fast twitch motor neurons. As a result of that, you lose connection to some of those muscle fibers. Some of those muscle fibers disappear, so they actually die off. You do have some muscle fibers that survive, and they survive because they're able to form connections with surviving motor units. So you get a reinnervation there, and then that changes to a slow twitch fiber because it's now receiving input from a slow twitch motor neuron. So what's happened in this whole process here is that you have a reduction in motor neuron number, a reduction in muscle fiber number, a reduction in the average size of the motor neuron, but you can see that you've actually increased the average size of the remaining motor units. So this one now has 3 muscle fibers instead of, or sorry, it now has 4 muscle fibers. It started off with 3 muscle fibers. So that's one characteristic with aging, and they can measure your motor unit size can actually be measured non-invasively. So this is a kind of a review of your fiber types, and the question here is, which fiber types would increase with aging? Because you have this reinnervation, this denervation, reinnervation process going on, the fiber types you see increase with aging are all the transitional ones. So you're getting conversion of, if you go back to this example, you're getting conversion of a fast twitch fiber to a slow twitch fiber. So with that conversion process, you see a lot of the intermediate muscle fiber types start to show up. So in a typical muscle, you have a high proportion of type 1 fibers. You have a mixture of type 1, type 2A, and in humans, type 2X. So in a typical human muscle, you kind of have a mixture of type 1, your 2As, your 2Xs. So those are the muscle fibers you see in the greatest proportions. When you start to age and you have this denervation, reinnervation process going on, you start to see those muscle fiber types that have a mixture of myosin heavy chains. They're termed your transitional fibers. So between the type 1 and 2A, you start to see your type 1C and your type 2C. And then between the type 2A and type 2A and type 2X, you start to see like the type 2AX. So the differences between 1C and 2C, so this is a bit of a review from last day, is again, they have a mixture of myosin heavy chains. These fiber types have a pure type of myosin heavy chain. So type 1s would have all myosin heavy chain type 1, 2As would all have myosin heavy chain 2A, and 2X has all myosin heavy chains 2X. The type 2C has a mixture of, it's mostly myosin heavy chain, so MHC stands for myosin heavy chain. It's mostly myosin heavy chain 1, but some myosin heavy chain 2A. And then 2C is more of a faster fiber type. It's kind of the reverse. It's got mostly myosin heavy chain 2A, and then some myosin heavy chain type 1. And the 2X here, that's between the 2A and 2X fibers, these fibers would have a mixture of myosin heavy chain 2A and myosin heavy chain 2X. So these are the fiber types, these kind of weird fiber types that have a mixture of myosin heavy chains. Those are the ones you see start to increase as someone goes through the aging process, because you're getting this transition between the major fiber types.